Hey everyone, this is it, last lecture of Math 206. So let's get right to it. We've been talking about this idea of inner products, right? We know that it allows us to think of length and distance and angles between vectors. And now we're going to see one important application of inner products. So we start off with a definition. In an inner product space, say V, a set capital S equal to, so this is just some collection of vectors, V1 up through Vn. And there's two parts of this definition really. So the set is orthogonal if every vector is orthogonal to all the other vectors. And so that would go something like this. If the inner product of Vi with Vj is equal to 0 when I is not equal to j. So whenever we take two distinct vectors from the set, take their inner product, if we get 0, that means that they're orthogonal. If you run through all possible combinations of v sub i's with v sub j's and get 0 each time, then we say that the set is orthogonal. Now there's a little bit more, so if, in addition, the norm of Vi is equal to 1 for each I between 1 and n, then S is orthonormal, right? So an orthonormal set then is an orthogonal set in which every element in there has norm 1, right? So it's a collection of length 1 vectors. Okay, so orthogonal and orthonormal, those are the topics, the terms that we're going to be interested in today. Now, okay, so now let's discuss what this, what these terms can do for us or what they mean to us. So suppose let's say S equals V1 up through V sub n. I want this to be an orthogonal set, so this is orthogonal. And I want to make sure that none of these vectors are equal to the 0 vector, so where no v sub I equals the 0 vector. Now, suppose that we have a linear combination of these vectors equal to 0. So if a1 v1 plus dot 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 plus a sub n v sub n is equal to 0, then we have, so I want to do a little computation here. 0 is equal to 0 vector dot v sub I, right? If you take any vector and do the inner product with the 0 vector, you get 0, right? That's one of the rules, the properties of inner products. Now, I can substitute this linear combination right here, this sum, in place of 0. So this is equal to a1 v1 plus dot 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 plus an bn comma v sub I. So I'm just substituting here. Now, we know that inner products satisfy the distributive property, and so this is going to equal a1 v1 inner product with vi plus that'll be a2 v2 dotted, or inner product with vi. Eventually we'll get to v sub I, so this will be a sub I v sub a sub I v sub I with v sub I, and then we keep going. Eventually we'll get to inner product of a sub n v sub n with v sub I. Right? So all I've done is done the distributive property. Each of these terms within the summation, inner product with v sub I. Okay, now we know that we can pull constants out, so this will be A1 times V1 inner product with VI plus dot 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 plus A sub I V sub I V sub I plus dot dot dot. Pull out the A sub n, and we'll have V sub n inner product with V sub I. Now, we know that our set is orthogonal, which tells us that the inner product of V1 with VI, that's equal to 0. All the way down, in fact, all of them except this term are going to be 0, right? So all of this stuff will be gone, and we're left with AI times VI inner product with VI equal to 0. So let's write that down. So we have 0 equal to A sub I times V sub I V sub I. Now, so we have this product, this number times this number equal to 0, and we know, we said a minute ago, right, none of the V sub i's are equal to 0, which means that this inner product is not equal to 0. That forces A sub I equal to 0. So we conclude that A sub I is equal to 0. Now, we could do this for any one of those A sub i's, so what that allows us to do is conclude that each one of those coefficients has to equal 0. And so, we just proved a theorem here, so let's write this as a theorem. If S is orthogonal, then, let's see, what did we show? That if we have a linear combination equal to the 0 vector, then all the coefficients have to equal 0. What we just showed then is that this set right here has to be linearly independent. So if S is orthogonal, then S is linearly independent. So orthogonal sets are linearly independent. Now, our interest is going to be in orthogonal and orthogonal or orthonormal bases. So let's just say our interest is in orthogonal slash orthonormal bases. All right, so that's what we're going to be looking at. So let's just look at a couple of examples first. So in P2 with the standard inner product, I want to look at the following set. So this is going to be the set. So let's let S consist of the polynomials x, 1 plus x squared, and 1 minus x squared. Now, you can quickly check, right? Take the inner product. So I mean, let me do one of these. So since note that when I look at x inner product with 1 plus x squared, that's equal to 0. X with 1 minus x squared inner product equals 0. Also, 1 plus x squared inner product with 1 minus x squared also equal to 0. So what we have here is an orthogonal set. So S is orthogonal. by our previous theorem, that tells us that this set is linearly independent. So by the theorem, S is linearly independent. Now, the dimension of P2 is equal to 3. We have 3 linearly independent vectors in our space that has dimension 3. That tells us then that S is a basis. So since the dimension of P2 is equal to 3, S is a basis. One thing to be aware of. What do I want to say? Oh, right. So if V is not equal to 0 vector, we can normalize, meaning that we can define the vector u equal to 1 over the length of v times v. And this vector right here will have length 1. In other words, we can quickly convert an orthogonal basis, or any orthogonal set, right, as long as we have non-zero vectors, we can convert that to an orthonormal set by just dividing each one by its own length. So, let's see what, let's call it T equal to, okay, so what are the lengths of each of these? Well, the length of x is just 1. The length of these two are root 2. And so the set consisting of the vector x, 1 over root 2 plus x squared over root 2, and 1 over root 2 minus x squared over root 2. This is an orthonormal basis for P2. All right, so you can quickly convert an orthogonal basis into an orthonormal basis, or set, in fact. Now, we want to see why we actually care about orthonormal bases. Yeah, so let's do it like this. So suppose, let's just look at orthogonal first. So suppose S equal to V1 up through V sub n is an orthogonal basis for this inner product space V. And let's choose some vector. So let's say, and let x be any vector. So just let x be in V. All right, so we've got some vector. Well, okay, what does that mean? So then there exist unique numbers a1 up through an, a1 up through an, such that our vector x can be expressed as a linear combination of our basis vectors, so such that x equals a1 v1 plus dot 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 plus an vn. Right. Now, if we look at, let's look at x inner product with v sub I. Now I'm going to substitute, so that's a1 v1 plus dot 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 plus an vn, and that's all inner product with vi. That's equal to, so now what's going to happen when you take the inner product of a1 v1 with vi, you get 0. a2 v2, the only one that's going to give us a non-zero entry is when we have the ai vi, so this will be inner product ai vi with vi. And so that's equal to ai times the norm squared of vi. And so now we can solve, so we can say thus, a sub I is equal to the inner product of x with vi divided by the norm squared of vi. So this tells us exactly how to express x as a linear combination of the basis vectors. It tells us exactly who the coordinates are for our element x, our vector x. And so let's collect this. I want to write this as a theorem now. All right, so theorem. So let's let S be a basis for our inner product space V. I need to write out S. So S is going to look like this. S equals V1 up through Vn, be a basis for S. Two parts of this theorem. So first, if S, so if S is orthogonal, then, let me say this a little bit less sloppy. So we've got a basis for S, and, sorry, I'm being totally sloppy. Let me start over. The theorem says let S equal to this set be be a basis for V, and let X be in V. Sorry, I'm going to get my first sentence right. So we have a basis for our inner product space, and we've chosen some vector X in V. So now if S is orthogonal, then our computation right here told us exactly how to express X as a linear combination of the V's. And so it would look like inner product of X with V1 divided by the norm squared of V1 times V1 plus dot 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 plus X inner product with Vn divided by norm squared of Vn times Vn. So it tells us who the coefficients are. Now, part B of this theorem shows why an orthonormal basis is especially nice. So part B, if S is orthonormal, then, so remember, orthonormal means orthogonal plus each of the vectors has length 1, or norm 1. So if each vector has norm 1, then all these norm squareds are equal to 1. And so then it would say X is equal to inner product of X with V1 times V1 plus dot 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 plus X inner product with V sub n times V sub n. So when you have an orthonormal basis, expressing any vector as a linear combination of the basis vectors is very easy. To find the coefficients, just take the inner product of X with each of the basis vectors. So let's do a quick example using the orthonormal basis that we concocted a few minutes ago. So let's say t, this is the one that we called t a minute ago, and so that's going to be x 1 over root 2 plus 1 over root 2 x squared, and 1 over root 2 minus 1 over root 2 x squared. So this is an orthonormal basis. Orthonormal basis for p sub 2. And what I'd like to do, so I want to compute the coordinates relative to t of the following polynomial: 2 plus x, 2 plus x plus 3x squared. All right, so we're going to do that relative to t. So how do I do that? What is this asking us for? It's saying, how do I express this polynomial as a linear combination of these three polynomials? So what does our theorem tell us to do? It says, let's do 2 plus x plus 3x squared, inner product with x. And by the way, remember, unless otherwise specified, we're working with the standard inner product. So the inner product here, that's equal to 1. Okay, so next we want to do 2 plus x plus 3x squared inner product with 1 over root 2 plus 1 over root 2 x squared. That's going to be, what, 2 over root 2 plus 3 over root 2, so that gives us a 5 over root 2. And then for the last one, we do 2 plus x plus 3x squared inner product with 1 over root 2 minus 1 over root 2 x squared. And this will come out to be 2 over root 2 minus 3 over root 2, so that gives us a negative 1 over root 2. So the coordinates are equal to 1, 5 over root 2, and negative 1 over root 2. So if you want to express this polynomial as a linear combination of these three polynomials, you do it by taking this polynomial plus 5 over root 2 times this polynomial minus 1 over root 2 times that polynomial. Okay, now, so we've seen an example. We see why it might be nice to have an orthogonal or orthonormal basis. The question is now, if you've got a vector space, is there actually such a thing? If you have some vector space, do you have, and we know we have a basis, do you have an orthogonal or orthonormal basis? And it turns out for finite dimensional spaces, the answer is yes. Okay, so it goes like this. So if V is a finite dimensional inner product space, then V has, I guess I want to say, well, let's say it like this. V has an orthogonal basis. And once you have an orthogonal basis, by just dividing each of those basis vectors by the norm of itself, each one, that converts it to an orthonormal basis. So it has an orthogonal basis, and I'll say hence an orthonormal. Basis. Okay, we want to prove this theorem now that tells us that if we have a finite dimensional inner product space, then we have an orthogonal basis. And so the proof, in this case, the proof is the key here. It's going to tell us exactly how to find an orthonormal basis for any finite dimensional vector space. So the process, this actually has a name, so this is called Gram-Schmidt orthogonalization. Right, and so this is a process of arriving at an orthogonal basis for an inner product space. So it goes like this. So let's let S equal to U1 up through U sub n be a basis. For capital V. What we're going to do is we're going to use this basis to build an orthogonal basis. So we construct an orthogonal basis, which we will call capital T, and it will consist of the vectors V1 up through V sub n as follows. Okay, so what I need to do is tell you who V1, V2, V3, and so on are, right? And once we get to Vn, then we will have created a new basis, and this basis will consist of orthogonal vectors. So it goes like this. First of all, V1 is exactly equal to U1. So for the first vector, they stay the same. The next one, so now we need to say who V2 is, and V2 is going to equal U2 minus U2 inner product with V1 divided by the norm squared of V1 times V1. Is that all right? Yeah. Okay. Now I need to tell you who V2 is, who V3 is, and from here, hopefully you'll see what the pattern is. So V3 is going to be U3. So we take the third vector in our original basis, and then we're going to subtract off some stuff, and the stuff will be U3 inner product with V1 divided by the norm squared of V1 times V1 minus inner product of U3 with V2 divided by the norm squared of V2 times V2. And so, I mean, I just want to say etc. here. The pattern continues. So if you want V sub 4, it's going to be U sub 4 minus, and then there'll be 3 pieces to subtract. It will be U sub 4, and then everything else stays the same. So put a U sub 4 in each of those spots, and you do the inner product with each of the basis vectors that you created before, divide by the norms, multiply by the vectors. Okay, so let's see this in action now, right? But there's the proof. You can check that this actually is an orthogonal basis. The idea is you start off with this original basis, and then you subtract off the portion that's making it not orthogonal, right? And you create this new vector, and you can check that. If you take the inner product of these two, you will get 0. Take the inner product of this and this, get 0. Inner product of this and this, you get 0. It's rigged to work. Okay, so let's try an example. All right, so it goes like this. Let's let W be the subspace of P3 consisting of all polynomials, so they'll be of the form a plus bx plus cx squared plus dx cubed. So here's the form of a general polynomial in P3, such that uh, 2a plus b plus c minus d equals 0. You can check that this is a subspace, and I'm just going to write down the answer for a basis here, so so you can check that the following set of polynomials is a basis. This is a three-dimensional subspace, so it'll be 1 plus 2x cubed and x plus x cubed and x squared plus x cubed. You can check that this is a basis for W. What I want to do now is I want to find an orthogonal basis for W, right? This basis that we have here, so let's call this one S. This one's definitely not orthogonal, right? And we want to use Gram-Schmidt to concoct an orthogonal basis. So I'm going to kind of work right above here, so I'll leave the formula to kind of see who the pieces are as we go through this. Okay, so let's call this one, so this is going to be my U1, this is going to be my U2, and this is going to be my U3. Okay, and then we're going to create, so first I'm going to create V1. V1 is equal to U1, so that'll be a 1 plus 2 x cubed. Oops, plus. Something's not right here. Oh, wait, no, because you subtract, right? 2 times that one minus that. Sorry, for a second I spaced out. Yeah, no, so here is my first basis vector. Now, V2 is going to be, so let's look at the formula. I take U2, so that's x plus x cubed, and then I subtract off U2 inner product with V1. So, and I'll write out all the pieces here. So this is going to be U2 is x plus x cubed, inner product with V1, which is 1 plus 2x cubed, divided by the norm squared of 1 plus 2x cubed, times the polynomial 1 plus 2x cubed. So let's see what we get here. X plus x cubed minus, okay, so I need to compute, oh, that should be norm squared right there. So let's compute the inner product. We're using the standard inner product, and so what we're going to get is a, looks like just 2 in the numerator. And then the length of this, that's a 1 plus 4 is 5, so 5. Right, the norm of that vector is root 5, we square it, so we get 2/5. And let me just keep myself honest with my arithmetic. Okay, and so that will be times 1 plus 2x cubed. And so this will be negative 2/5 plus x. Then I'm going to have x cubed minus 4/5 of x cubed. So I think, yeah, so that should be a plus 1/5 x cubed. Yep. So here, I'm going to circle these. So here's polynomial 1, and there is polynomial 2. That's my v sub 2. All right, now, so let's leave that formula up here. Let's find v sub 3. So v sub 3 is going to be u sub 3. So that's x squared plus x cubed. X squared plus x cubed. Minus, okay, so now I'm going to do inner product x squared plus x cubed with v1. So that's a 1 plus 2x cubed divided by the length of 1, I know I'm repeating myself now, 1 plus 2x cubed squared times 1 plus 2x cubed. Minus, okay, so now we're going to do u3 x squared plus x cubed inner product with v2. So notice you have to compute v2 before you can go on to the next step. And so this will be with negative 2/5 plus x plus 1/5 x cubed divided by the length of v2, sorry, length squared of v2, and sorry, I ran out of room, but now this is going to be multiplied by u2 or v2, so I put it right in there. Okay. Now, I won't make you go through the arithmetic, but I actually did this. And you should notice Gram-Schmidt can get messy very quickly. So on an exam, I'm not going to have you do something that gets super messy. But you do need to be able to keep your head straight and crank this out, right? Computers nowadays obviously can compute this very easily. So if you multiply this out, here's what you get. Negative 1/3 minus 1/6x plus x squared plus 1/6 x cubed. Okay, so there is my vector v3. Take these three together, that forms our orthogonal basis T. So it is a little bit time consuming, it's a little bit tedious, but you want to understand that there is a process. If you start off with any finite dimensional vector space by first finding a basis, you can then tweak that, convert it into an orthogonal basis. All right, that's it. Congratulations, you made it through. I know this coronavirus quarter has been very odd, very difficult. Hopefully you've been able to learn something. I know it's hard. It's really sucks here for me to stand up and teach in front of a camera rather than in front of you. But we've all done our best, done the best that we can. So that's it. You survived Math 206. All you got to do is get through the final. All right, so we will see you. Remember, there's a review session on Friday, and then the exam is 1 week later. I guess that must be June 12th, so Friday, June 12th. All right, we'll see you later.